Okay, this is the examples and practice video for lesson 11, which is about transforming and combining distributions. This section is pretty much specific to AP statistics courses. So let's take a look at some problems. I have a small number of problems here just to illustrate kind of a breadth of ideas. There's a lot of things you can do here, but this is kind of the main ideas. First problem says the Attila Barbell Company makes bars for weightlifting. The weights of the bars are independent and are normally distributed with a mean of 720 ounces and a standard deviation of 4 ounces. The bars are shipped 10 in a box to retailers. The weights of the empty boxes are also normally distributed with a mean of 320 ounces and a standard deviation of 8 ounces. How will the weight of the full boxes be distributed? So pause this and give this one a try. Okay, so I like to do a couple things when I'm solving a problem like this. First of all, I like to just kind of come up with an algebraic expression that talks about what's going on here. So what we really have is we have an empty box, right? And then we're going to add to that 10 bars. Bar, 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 and there's 10 of these. There's 10 of these bars, right? And that's going to make up what I'm going to call a FB, a full box. So the empty box plus 10 bars is the full box, okay? Well, every one of those individual elements, the empty box from box to box will vary, and each one of the individual bars will vary. So if you think of them as having a distribution, right, this is a normal distribution, and they said the empty bars are I'm going to omit the ounces here, so there's units throughout. So there's 320 ounces with a standard deviation of 8. And then this first bar here, right, also has a variance, right? It's centered at, it's 720 ounces with a standard deviation of 4, right? And then the next bar also is centered at 720 with a standard deviation of 4, and so on. That will eventually, so there's 10 of those, there's 11 sources of variation here, and they all add up to a distribution for the full boxes. And what we're after is to figure out the mean and the standard deviation for the full box distribution. That's what we're after. Okay, so there's a picture of what's going on. So the first thing to know is that when you're talking about the means, there's no variation in the mean. The mean is a known quantity. So that means that the mean will always exactly follow whatever the algebraic expression is for that. So I could write it this way. For the means, the mean of the full box is going to be equal to the mean of the empty box plus the mean of one of the bars plus the mean of another bar, and so on, right, accounting for the fact that there are 10 bars in there. So the way I could write it maybe is this. The mean of the full box is equal to the mean of the empty box plus 10 means of the bars. I'll just now make that a multiplier. So the reason there's a 10 here is because I'm adding up 10 individual means of individual bars. Okay, and so that means that the mean of the full box is equal to the 320 ounce mean of the empty box plus 10 means of the bars, which are 720 each. And if you compute that in the calculator, it turns out the mean of the full box is therefore equal to 7,520, and now I'll put that this is ounces. So the mean would be 7,520 ounces. Okay? So the mean is usually pretty straightforward. We just copy the algebraic expression. Okay. Now, when it comes to variance, the variability, we're going to deal with all these standard deviations, right? And they also sort of follow the algebraic expression. There's a couple differences to keep in mind, though. One of them is that we can't add directly the standard deviations. It's the variances that add, okay? The variances add. And then the second thing is that even if we have subtractions in the combination algebraic expression here, variances always add, because every time I add another source of variation, whether I'm multiplying by a negative or not to make it a negative, it's still adding variability to the overall structure, right? So you can structure something like this algebraic expression, but talk about variances. So I'll put the standard deviation of the full box squared, that's the variance of the full box, is going to equal the variance of the empty box plus the variance of one of the bars, plus the variance of another one of the bars, plus the variance of another one of the bars, and there are 10 bars, so there'll be 10 of those variances, right? Just like there were 10 means. Okay, so you have the variance of the full box, standard deviation squared, is equal to the variance of the empty box plus 10 of these variances of the bars. So I could use that right there. Now let's plug in what we know, right? We're still trying to find the variance of the full box. So the standard deviation of an empty box is 8, so this would be 8 squared, and then we'll have 10 of these 4 squareds, right? The standard deviation squared, so the variance is there. And that just means that the standard deviation of the full box is going to end up being the square root of 8 squared plus 10 times 4 squared, right? Which turns out to be the square root of 224, right? Or 14.966 ounces. So that will be the standard deviation. So the way we could write this, if we wanted to use kind of another notation, that the weight of the full boxes will be distributed according to a normal curve, where the mean is 7,520 ounces, and the standard deviation is 14.966 ounces. Okay, so that would really be the way to write the answer, right? It's a normal distribution with that given mean and standard deviation. All right, so let's try the next problem. It says for graphic design work, a particular graphic designer charges $50 per hour plus a fixed setup charge of $200. If the time required for graphic design jobs varies normally with a mean of 30 hours and standard deviation of 14 hours, then how does the distribution of charges per graphic design job vary? So pause this and give this one a try. Okay, so this is actually the other kind of problem. Instead of combining multiple distributions, this is about taking a single distribution and transforming it in some way. So the way I could say this is we're going to start with a distribution for hours, and we're going to transform it into a distribution for cost or for charge. Right? So we have for the hours, that the hours are, we have a mean of 30 hours with a standard deviation of 14 hours. Okay? And we know that after we transform, that will have some mean and standard deviation as well. And our goal is to figure out that distribution right there. So what is going to happen when we try to transform hours into cost? Well, we could create a formula for that. We could say the cost is $50 per hour, so it's 50 times the number of hours plus a fixed setup cost of $200. So what's happening here as we transform is we're taking the number of hours and we're multiplying by 50. So we're multiplying by 50 and we're adding 200. So there's a multiplication step and there's an addition step here. All right. So the thing to remember is that multiplications affect everything, but additions only affect measures of center. They don't affect measures of spread. So the way I could think of this is that the mean of the cost, right, is going to be, it's going to be the 50 with the multiplier. That's going to affect everything. So 50 times the mean of the hours, right? And additions, right, those are shifts, and those things do affect measures of center. So that would be, we would add the plus 200 on there. So both the multiplication and the addition affect the mean, right? But when I compute the variance, or the standard deviation, if I talk about the standard deviation, right, the standard deviation is affected by the multiplication, but the plus 20, the plus 200, that's a shift, and shifting data does not affect its width, right? So we will have the 50 multiplier for the standard deviation, but the plus 200 will not appear in that formula, right? Multiplication affects both measures of center and measures of spread, but the addition only affects the measure of center. So now we can compute these. If you just plug these in a calculator, this would be 50 times the previous mean of 300 plus 200, and that turns out to be a mean of $1,700, right? And then the standard deviation for the cost will be 50 times the standard deviation of the hours, which turns out to be 14. So this ends up being $700. Right, so what this is a normal curve with a mean of $1,700 and a standard deviation of $700. So this would be 1,700 here and 700 here. Okay, so the thing to remember is that multiplication affects everything, but shifting, adding, and subtracting, that only affects measures of the center. Okay, let's take a look at another problem here, just two more. Suppose that in a particular nightclub, the heights of men and women were each normally distributed. Men's height had a mean of 69 inches, standard deviation 5 inches, and women's height had a mean of 64 inches, standard deviation of 4 inches. If one female and one male were each randomly chosen and paired to dance, what would be the probability that the woman would be taller than the man in that partnership? So go ahead and pause the video and give this one a try. Okay, so we're talking about the difference in height, right? Because for the woman to be taller than the man, we're going to be comparing the heights, right? And a good way to compare here would maybe be just to subtract the heights, right? So the way I'm going to do this is I'm going to define a new variable. I'm going to call it D for difference, and I'm going to define it as the men's height minus the woman's height. The men's height minus the woman's height. So if the man were taller than the woman, it would be positive. But if the woman were taller than the man, so if the woman is taller, that means that D is negative. So I'm defining this D so that it'll be negative in the case that the woman is taller than the man. Okay. So what I've really got is a case of two different distributions, right? I have a distribution for the men, for the males, okay? That's centered at 69 inches with a standard deviation of 5 inches. And I have a distribution for the women that's centered at 64 inches with a standard deviation of 4 inches. And if I subtract, if I take a man's value minus a woman's value in height, then I'm going to get my difference distribution, right? Men minus women is how I defined it. And that will have some mean and standard deviation. Okay? So my first job is to figure that out. Okay, so I'm going to use the rules that we said before. If this is the algebraic expression of what the difference is, then I could say, all right, I know that the mean of the D is just going to be an algebraic expression of the mean of the men minus the mean of the women, right? That just follows whatever the algebraic construction of the random variable is. So this would be men's mean is 69, women's means are 64, and so the mean of the difference would be 5, right? 5 inches. And so this right here is 5, okay? All right, and then as far as the standard deviation, we're going to take variances, right? So the variances of the difference, that would be equal to the variance of the men, and then the variance of the women. But even though this is subtraction, every time I add a new source of variability, it always increases the variability. So that will be a plus there, even though the algebraic expression contains a minus. All right, so that means that the variance of the difference will be the standard deviation squared for the men plus the standard deviation squared for the women. And that means that the standard deviation is the square root of 25 plus 16, right, which would end up being the square root of 41, which is 6.4031 inches. Okay, so this one, these variances here are 6.403 approximately. Okay. Okay, so the first part of the problem is to define the mean and standard deviation. Now the second part says, what's the probability that the woman would be taller? So let's extend the page here and we'll work on that as well. Now we've got a distribution here for this D variable, the difference. And we now know that the mean is 5 inches and the standard deviation is 6.4. I'm just going to round it to 6.4. Okay. So we said we want the probability that the woman is taller. Okay. And what that means is we're finding the probability that this D variable is negative. Okay, so if I were to write that this is 5 plus 6, this would be about 11 here, 11.4. And if I took 5 and subtracted 6.4, this would be about negative 1.4 here for this d variable, right? So that means that there is some place here where the difference is 0. And anything where the difference is negative means the woman is taller. So I'm just finding the area under that normal curve. That means we can find that by using normal CDF, right? From a lower boundary of negative infinity, I'll use negative 999, up to an upper boundary of 0 if the mean were 5 and the standard deviation were 6.4. Right, so we could use a calculator now to find that. We can say, what's normal CDF? Lower boundary, negative infinity. Upper boundary, 0. And then mean is 5 inches, standard deviation 6.4 inches. Okay, and that turns out to be 0.2173. So, what's the probability that if I randomly pair a man and woman from these groups, that the woman will be taller? That'll happen approximately 22% of the time. All right. Okay, last question. This one says, you learn that your company is sending you and several other employees to staff a new office in China, where everyone will earn the equivalent of their current salary, but converted to the Chinese currency, the yuan. Each US dollar is worth 6.84 yuan. In addition, everyone will earn a fixed weekly travel living allowance of 300 yuans. Below is a table that shows some statistics for the weekly earnings of the group that's being sent overseas now in U.S. currency. Could we fill in the corresponding values in the group that they will earn in China? Okay, so pause this, give it a try. All right, so what I would do probably is just say, let's make an algebraic expression here. In general, the Chinese amount that we earn is going to be the US amount times, let's see, US dollar is worth 6.84 yuans. So for every US dollar, if I multiply by 6.84, I'm going to get the number of yuans. So if I take the US salary times 6.84, that's the conversion. Plus we have a fixed additional 300 yuans in yuan currency. So that's kind of an algebraic expression. So we're multiplying the US number by 6.84, and then we're adding 300. Right? The thing we have to remember is the multiplication, this affects everything, right? Both measures of center and spread, but the shift, right? The shift only affects measures of center. Only measures of center, not measures of spread. Okay, so if I look at these statistics, a minimum salary, that's an individual data value, right? So that's just an individual point. I'll call it a point, right? The maximum salary is a point. The median salary is a particular measure of center. It's like an individual point. The mean salary is a point. So those are all like measures of center or individual data values, right? But the salary standard deviation and the salary IQR, those things are measures of spread, right? So if I'm converting these things, I think what I'm going to do is, if I'm talking about things that are individual data values, like means, medians, or individual salary values, I could just apply this formula to each one. So I could, for example, say that the corresponding one here would be 6.84 times 500 plus 300. And that would give me the value yuan 3720 there for this one. If I did the same thing, 6.84 times 3,000 plus the fixed allowance of 300, that would give me 20,820 yuans, right? And this one here would be 10,833.6 yuans, right? I'm just applying this formula and plugging these values in for the U, and these would be the corresponding C's. Same thing here, right? I would plug 1,910 into for the U, multiply by 6.84, add 300, and the result should be 13,364.4 yuans, okay? But when I come to these measures of spread only, I'm only going to multiply by 6.84. So for example, I would say this is 6.84 times 300, and I'm not going to add the additional 300 because that shift will not affect the standard deviation, this measure of spread. So this would be 2,052 yuans for this. And this one would be 6.84 times 550, or yuan 3,762. So the key idea here is that measures of spread are only affected by multiplication, but individual points, including measures of center, mean and median, but also individual salaries like max, min, or anyone's individual salary would be affected by both the multiplier and the shift. All right, there are other things you could do with these ideas, but this was intended to be a cross-section of the kinds of problems that you can do that either involve transformations or multiplication. So if I scan back through this real quick, this first problem had empty boxes and bars being combined. So those were combinations of different distributions, right? This is where we had to add variances, right? And the means followed that. Also, in problem 3, that was something where we made a difference that was a difference in heights that were by combining the male and female, right? So we have variances adding in this case, right? For problems 2 and 4, we were taking one distribution and transforming it by multiplying or adding and subtracting. So hours were being transformed into cost in problem 2, and that meant that we didn't work with variances. We just strictly work with the standard deviations, but we only apply the multiplier, not the shift. And then problem 4 also was a single distribution US that's transformed to China numbers, and that means that individual points are affected by everything, but measures of spread are affected only by the multiplier. All right, so that concludes this video.